If you have been feeling very comfortable so far in chapter 3, it is actually quite normal because all these things are quite straightforward. The coming last part will be the hardest, the most challenging part in chapter 3, and probably the only challenging part actually. But once you understand the whole idea, it should not be too difficult for you. Okay, so let's get started. If you're an HL student, I recommend you to read it by yourself. You may want to pause the video, and if you're an HL student, I can just explain to you directly. So earlier we talked about ideal gas law, and one of the assumptions that we talk about is they move in random direction and also different speed as well. So just like how statistic or population were distributed, there's something called normal distribution. If you learn about that in statistic and maths, then you know they all will follow something called the normal distribution, which most of the people or whatever particle will converge in the middle, and on the two end it will be less, will be very extreme, and you find a more rare case there. So the other thing that we usually do for statistic is that we could calculate a certain values average by simply adding them together and then divide by the number of the unit that you are having. So this is the usual way that you calculate average, or we call it mean in mathematics. However, if we want to represent average kinetic energy, using this would make it quite tricky, because you know the KE equation is actually half mv squared. So it will be quite tricky to express because v is in a form of square. So a new concept that is you may call invented by the mathematician is, or physicist, is called the root mean square speed. So the word RMS stand for root mean square. So basically you could refer this as its name simply. Root actually means that you can see the root here, and then mean is like you have to divide by the like how many units are there. Square is simply you would square all of them, and it looks very daunting and scary, right? But the interesting thing is, once you defined the root mean square speed like this, then when you express the average kinetic energy as like below, then you can get a very nice expression. When you try to take all the squared out, then the C will simply be C squared, like the one that we defined here, because when you square it, then you can get all these things inside, like how we extract it here. So in that way, it will be much easier to express if we defined the C this way. It's nothing more than the definition to make us to do it more conveniently. If you are studying HL physics, then you will see this again, or you should have already seen it in chapter 11 already. The main point of this part of video is actually not about that, but I'll try to go through with the textbook process. But the main reason I'm making this part of video is later on you need to use an equation called P equals to 1/3 rho, which is density, times C squared. So in the textbook it only said it is been proven already, and then you later on use this for like some other things to prove further on, to prove a equation that you actually use. But then as a physics student, I would strongly encourage you to continue this video and try to understand how we actually prove this, instead of just saying, oh, someone already proved it. And this is exactly what I was talking about a few parts of video earlier, that how come you need those assumptions, and this is actually start from here. So stay tuned and I will explain to you in a second. Okay, so let's get started. The equation that we are going to talk about once again is called the kinetic theory formula, and the equation itself is written here. P equals to 1 over 3 rho c squared, while P stands for pressure, rho stands for density apparently of the air, and c stands for the root mean square speed, which we defined earlier. And once you get this, then you should be able to get the other one. So let's just focus on this one first. This equation is actually proposed by Maxwell. If you heard about Maxwell, he was also one of the greatest scientists in the history who made the Maxwell equation, Ford equation, which unified the electric field and magnetic field. And you may just simply call him a genius. So he should be as famous, although he may not be in, maybe when you may not know about his name in primary, but then he should deserve the same amount of honor as Einstein and Isaac Newton as well. And if you remember what we talked about ideal gas law, the equation here we only apply to ideal gas law, ideal gas again, and therefore we need assumptions. And the following, that means the equation here, it does not apply to solid or liquid, okay? So only for ideal gas. And the assumption is in fact very similar to what we mentioned earlier, and let's just go through it again for a quick revision. Let's say first of all, the molecules would have elastic collision. You can also imagine they are hot. That means the impact time, if you remember, the impact time will be very, very small, and then it is elastic collision, so there's no energy loss. Second one is that it is a continuous random motion, which is of course something that we will need to use later on as well. So they don't go in the same direction, and they all simply go all evenly random direction. The second thing that we find out would be, I think this is not assumption, but more about the finding later on. The average kinetic energy of the molecule will be proportional to the absolute temperature. So this, I don't actually think it is an assumption, but we will find it out later on. The next one is the one that we mentioned earlier, that there will be attraction force between the molecules. If you remember the van der Waals force, and here we would need them to, this force needs to be insignificant, so we can ignore them, and we have mentioned the reason why before. So if you forget, you may want to visit that video again. The next one, which will be very crucial, is the volume of the molecules is this word may be a bit difficult, but it actually means infinitely small comparing to the volume of the gas. So I think it's gas container here, so there's a word missing, container. So like what we said earlier, that you have to have a tiny bitty ball, which are the particles, comparing to the whole length of the container. A contrast I can make is, let's say these two are actually a bit bigger, but then let's say the billy ball is like that big, the molecules are like that big, and so the traveling time will be a bit different when you go from one place to another place, because of the radius itself. So that will make a difference. The last one is the time span in the collision is much smaller, like what we said earlier. Actually, it was something to do with the word hard sphere here, compared to the time between the collision. So again, we mentioned this assumption earlier as well. So for now, if you're interested to prove the equation by yourself, you may want to pause the video and try it out yourself. If you want to continue, then just go ahead and go with us. So let's take a look here. Imagine you got a cubic box. That means each side with the same length, and each side you have L as the length itself. And So the volume will simply be L cubed in that case. And let's say there is a total of n, big N molecules, each of mass m, and let's the density of the gas to be R, or rho if you like to, and the velocity of each molecule will be u1, u2, u3 up to un, because there are n molecules. Consider a molecule moving in the x direction only, and then you can later on do for y and z direction since it's all the same. So let's just talk about x direction. So you can imagine like what we do just now. This is L, this is L, so basically a square, and then there's a particle that is moving towards the phase A, let's say this side, like this one, phase A, with a velocity u1, and the collision with the phase A molecule will experience a change of momentum equal to 2mu1, because when this particle collide with the phase, and since we already assume the collision is elastic, that means it would not take away any energy from it. So when the ball bounces back, it is gonna be the same speed, so u1. So when you calculate the change in momentum, then it's gonna be mu1 minus the negative mu1, and that gives you 2 mu1. Okay, next, this is a bit more complicated. Let's take a look of it one by one. When it travels back to the box, it will collide with the opposite phase and hit the phase A again after time t, where time t will be 2L over u1. So if you look at this diagram again, since the speed of this particle is always u1, then think about when you start to collide and then you go back again, you will travel, this particle will travel for a 2L distance, and therefore the time will simply be the distance over the speed, right? And in that case, this is how we can find the time between the two collisions of the same phase. Next, the number of impacts per second on same phase would therefore be 1 over t, because depending on how fast you are, if you go faster, then you may hit more times. The less you have, then will hit less time. But then since the time for one time, this is like, if you recall what you learned in waves, for example, this is like period, and therefore number of impact per second is like frequency. So it will simply be equals to 1 over period, and therefore it's 1 over t. And therefore, since period is 2L over u1, and this will be u1 over 2L, just reverse the fraction. Next, the rate change of momentum. So think about this. This is how many impacts per second, right? So this is a number of how many impacts, and each impact will give you a change of momentum that we found earlier, which is 2mu1, and so if you multiply that, then that equals to what we talk about here, which you may find the 2 will cancel out, and you will have mu1 square divided by L. So this is how you can get this expression, and that should equal to force, because if you remember what you learned in chapter 2, rate change of momentum equals to force, because F equals to ma equals to m delta v over delta t. So the thing at the top here is momentum, and therefore divided by delta t is rate change of momentum. So this is due to only one molecule, be careful. And since the area is L square, and therefore you can substitute the area with A, and for the pressure, we talk about in the last video, I said the purpose of introducing pressure equal to force over area in chapter 3 is right here. So A would then become L square, and F is simply what we have here. And when you substitute this into the equation, you will then get L cubed in the lower bottom side of the fraction. So this is how you can get it. However, there are a total of n molecules in the box, and just let's say, I know this is a bit crazy, but at the end when he tried to propose this equation, and we also did it with experiment, we find out it is really true. So bear with me. If they all travel in the same direction, then you have to multiply the whole thing by n apparently. But since they are of different velocity, so you're actually adding each velocity one by one. So you can see it's actually the same thing, mu1 squared divided by L3. So we can extract the m divide L to the power 3 over here, and you multiply with u1 squared plus u2 squared and so on. So that should be the total pressure on A when you have n particles. However, we all know that the particle will travel in three axes, which is x, y, and z, and therefore by averaging the result, we only get about 1/3, well, which if it's go evenly, that's why we need to make the assumption that they go in a random motion. So I hope you start to see the connection between the need of the assumption to our calculation, or not calculation, the deduction here. And therefore we would have the term 1/3 in the equation. So the 1/3 is actually meaningful. It's not like randomly you have to divide 3. And this is, I feel like when I was a student, when I learned this, I feel this is the craziest part basically. Like how can you make such a judgment or deduction? But it's actually really true experimentally. Later on we find out. So once you get this, basically the whole thing is almost done by now. Since we could rewrite the whole thing, because here we got m and then all these things, right? If you remember, this is basically the root mean square. Then we can rewrite n times c square as this whole thing. Alright, and we can then substitute the whole thing by saying pressure equals to 1/3, which is just copy this from here, and then m times the nc square over L cubed. So this is how you can get the equation on the left. Since the V here is actually same as the L cubed here, because this is the volume of the container, which is the volume of the gas also. Be careful when we talk about the volume of a group of gas. Basically we're talking about the space that they take up. So it's not like individual particle and then you add up that particular particles only. Just like when you talk about atom, we know atom, we have nucleus, including neutron and proton in the middle, and then the electron will be orbiting supposedly around the atom. And when we talk about the size of the atom, we actually talk about the whole thing, because in fact the nucleus take up very small space inside the atom, like 1% only. So if we want to talk about the size, we actually talk about the whole space that it take up. Okay, so let's see how this equation turned into the final equation here. So since we have in the equation the small m, which is one molecule's mass, and the big M, which is the total number of molecules, if you have that, then basically if you multiply them, it is the total mass of all the molecules in the gas. And since simply density equal to mass over volume, then you can convert these two together with divide V into rho. So that's why you get you maintain the 1 over 3 and the c squared, and then you get the rho out of it from these three things. And this is how you get the equation at the end. And that actually means the root mean square speed and also the density will have such a relationship with the pressure also. So that means when say the root mean square speed increase, that means temperature increase, pressure will increase also. Or if you're keeping the temperature remain constant by increasing the density, then pressure will also increase. And you can also visualize it by simply imagine the particle more dense particle, so you have more collision per second when you increase the density. Or when you increase the speed, you also have increased the frequency. That means the collision per second as well, and therefore increasing the pressure. And this is the relationship between these three variables. If you want to keep the equation like this, basically what you have to do is simply go back to this equation and put the V together with the pressure, and therefore you can get PV equals to 1 over 3 m and c squared. You can also write as PV equals to 1 over 3 big M, because you remember this is actually big M, c squared also. So this is also something that we may use later on in the textbook. And it is very important to identify for this M, which is total mass, while for this one is simply density, while earlier for the small m you only have one particular particle only. Okay, so that is all for the derived work of the kinetic theory formula. Again, if you are studying IB physics and if you find it difficult, that's very normal, and don't worry, this would not be on the exam, but I still believe if you can understand through the proof itself, then you will start to appreciate why we need all these assumptions.